Hi, everyone. Welcome to Cassandra Lunch. We are on Cassandra Lunch number 54. So we've been doing this for quite some time now. Today, Nikita will be covering machine learning with Spark and Cassandra. Nikita is a junior software engineer here at Anant. Your organizers for this event are Raul, Arpin, and myself. And we are always looking for more speakers and sponsors. So if you guys want to reach out to any members of your communities, anyone who you think would benefit from learning more about Cassandra, please feel free to reach out to one of us. Our emails are listed there at the bottom. You can just contact us and reach out if you're interested in speaking, have a topic you'd like to talk about, or know people who would like to sponsor this sort of event. We are part of a larger community, Data Community DC. And Data Community DC is an inclusive community. So all walks of life, gender, religion, race, sexual orientation, all of that is accepted here. So do feel comfortable. Data Community DC also is part of this larger community of all these other organizations, if you will, that all come together to form this larger Data Community DC. What we cover here, we cover all things related to Cassandra, which also includes DataStax, which is an enterprise version of Cassandra, including Spark, Kafka, and different ways they all connect. Sorry if you guys can hear my dog in the background. He decides to go crazy once I start talking, apparently. This is a point in the intro where we like to encourage people who are new to speak up. I'm gonna check. Doesn't look like we have any newcomers, so go ahead and move on. Group rules: if you have a question, go ahead and ask it. Be polite and courteous to others, and share what you know. This is meant to be a discussion. Sometimes the speakers do have their own rules in which they like to ask questions, which they'll cover when they take over. But typically the chat or unmuting yourself is going to be the way to go, as my dog continues to make more noise. Here at Anant, we do real-time data platforms. So any large or big data type platforms, analytics, that sort of thing, that's kind of our shtick. And DataStax is a close sponsor and partner with us as well. GWU as well, when we have in-person meetups, they typically allow us to host at their facilities, which is really kind of them. Hopefully we'll be able to get some of these started here soon, now that things tentatively are kind of normalizing. Some of our other program sponsors, as mentioned before, DataStax, Eastern Foundry. And these are some of the organizational sponsors for Data Community DC in general, which help sponsor things like pizza at those in-person meetups. 15-second announcements. Does anyone have anything coming up? Meetups, hackathons, job announcements? I'm gonna take that as a no. We are hiring here at Anant for full or part-time positions as data platform operator, engineer, or architect. You can find out more at careers.anant.us. If you or someone you know is looking for a job as one of these positions, definitely refer them to us. We are looking. Some upcoming Cassandra events. DataStax always has weekly workshops. This event itself is every Wednesday at noon. Data Engineers Lunch, the kind of like a sister event to this one, is every Monday. That's where we kind of cover more generic data engineering topics. Some upcoming topics we have for Cassandra specifically, migrating PostgreSQL to Cassandra. using Spark SQL, Parquet tables. I got this. Tables in DSCFS and DSE Analytics. I'll be presenting on that. So I better learn how to pronounce that soon. And then we also have a guest speaker coming in, first one in July, using secondary indexes in Cassandra. For more information on that, you can go to anant.us/events. All of these videos are recorded and posted to our YouTube playlist. If you go to YouTube, you can find it at Cassandra Lunch. If you search that, you should find this, and hopefully the data engineers lunches would come up in that search as well. Cassandra.Link is your #1 resource for all things Cassandra. You can see here in the screenshot, there's a bunch of things related to Cassandra as well, hand curated by Rahul Singh here in Anant. So definitely check that out if there's any topics related to Cassandra that you are interested in learning more about. And with that, I will pass it over to Nikita.
Thanks for the intro, Josh. All right, so I'm Nikita, a junior data software engineer at Anant, and I'm going to share my screen. Hopefully this is the right thing. It's visible, right?
Yeah, we can see it.
Okay, cool. All right, so let's go back. So today I'm going to be talking a little bit more about machine learning with Spark and Cassandra. I talked about this topic a few weeks ago at Cassandra Lunch 50. You can find the YouTube video of that along with the blog post and slides. Something in the chat. Audio seems too low. Is my audio too quiet or?
We can hear you okay.
It might just be on your end per mode. I'm not sure. All right. So I'm going to talk a little bit about some stuff that I already talked about in case you weren't at the last presentation. And then we're going to talk a little more in depth about a couple different machine learning algorithms and strategies. And then we're going to look at a demo which showcases these strategies and applies them to the same problem and see sort of how we do. All right, so what is machine learning? Machine learning is the study of computer algorithms that improve automatically through experience and by the use of data. It's seen as a part of artificial intelligence, and it's used in a very large number of applications in today's society in many, many different fields. And this is also always rapidly expanding. So I can't imagine in 10, 20 years if there will exist a field that doesn't somehow use machine learning. So some fields that it's currently used in nowadays include medicine for like drug discovery. So basically trying to figure out if you have like a particular set of molecules that you know are good at like suppressing some kinds of things or attacking other like things, then you can use machine learning to try and figure out what potential molecules could do similar things that we haven't created yet. That's pretty neat. Everyone probably has heard of like image recognition and various image recognition softwares, email filtering. So if you have a Gmail inbox, then they probably use some level of machine learning to filter out what's spam and what's not. Machine learning uses complicated mathematical concepts and systems, heavily focused on linear algebra, making it appear intimidating to many beginners. However, many open source and easy to access tools exist for working with and using machine learning in the real world. A couple of my favorites, or my personal favorite, is TensorFlow. And then today we're going to use a little bit of a Spark machine learning library, or MLlib. Additionally, many well-constructed resources exist for learning machine learning online. There exists plenty of basic machine learning courses on all sorts of like on Coursera, on Udemy, on a bunch of these like course sharing platforms. And then one set of lectures that I like in particular, but it's more theory oriented, is the Caltech CS 156 lectures, which you can find at that YouTube link. But it's quite a long watch. So the other thing I'm going to cover, we covered a few weeks ago, is sort of the 4 stages of processing data in machine learning, which is something that you'll see in pretty much every machine learning application or process or like demo software or anything along those lines. So the first portion is preparation of data. So we have to take our raw data. That could be like pictures, could be like various measurements of like certain levels of stuff in like water or like different beverages or something along those lines. And we convert it into data that may be labeled, and maybe we separate out some of our features and components that we care about training our model with. Then we want to split the data into different sets. Basically, it wouldn't be a very useful application of machine learning if you trained the data on some kind of, or if you trained your model on some one set of data, and then you also tested the accuracy of the model with that exact same set of data. In fact, sometimes you'll overfit. So even though you might get a really, really good like accuracy, so to speak, on your training set, then when you give it new data that the model's never seen before, you'll suddenly get extremely low accuracy. So you definitely want to have a training set or a testing set that's separate from your training set, so that you expose the model to new new data to try and make predictions about that new data. And then third portion, machine learning, is typically you train your model. So you feed it the data and then you let it do its magic. And then finally, you obtain predictions using the trained model with, well, some kind of new data. All right. So why use Cassandra when we're talking about machine learning, right? First main point is speed and reliability. So machine learning projects tend to involve processing very large amounts of data in order to properly train complicated models. Millions of points of data are necessary for high accuracy in many applications. And Cassandra is very good with dealing with large amounts of incoming data. That last part should be cut off. We're going to ignore that. And additionally, Cassandra is built upon a masterless architecture. There are no master nodes, and thus there is no single point of failure. Data in Cassandra is replicated and multiple copies are stored across more than one node, ensuring that availability of data, even when nodes drop from the cluster or unexpectedly shut down for whatever reason, which is what's really cool about distributed databases in general. And then scalability and upgradability. Cassandra can be scaled both horizontally and vertically. Horizontal scalability allows the addition of many weaker machines as opposed to upgrading to a significantly more expensive processor or more RAM on one machine. And so it's easy to scale up your performance with relatively little cost. All right. So the first ML algorithm, I guess we're going to talk about, is called the random forest. So the building block of a random forest is a concept known as a decision tree. So decision tree learning is a predictive modeling approach used in statistics, data mining, and machine learning. Given a set of data and labels to the data, we can build a decision tree to try and figure out how to separate the data into classes while testing on various attributes of the data. where every node in this tree is represented or represents an attribute that we test on. So for example, in this wonderful set of data where we have 2 red underlined numbers, or 2 red underlined ones, a red 0, and then 4 blue zeros. First attribute we may choose to test on is the number red or not? So we have yes and no. And then in the no category, we have just all blue zeros. They're all the same, so we're done. That's like one class. And then with our remaining data, we choose to maybe test, is it underlined? Or we could have also maybe tested like, is it a 1 or a 0 at this point? And that would separate out the data as well. And so our leaf nodes are the final classes that we've separated the data into. So in this case, we've separated our data into 3 separate classes by testing 2 different attributes. And so a random forest, as the name may suggest, consists of a large group of decision trees made with different segments of data. So suppose we have capital N pieces of data that have M or capital M different features, or sort of like individual like components of the like data. So like maybe like the height of a person, the weight of a person, those would be our features. So we arbitrarily select to make lowercase n decision trees as part of our random forest. For every initial input into the random forest, or into each of these individual little decision trees, we take a sample of size big N from our data, which is size n. But what we do is we take these samples with replacement. And so the reasoning for why we intentionally take out some pieces of data and add in copies of other pieces of data is a little bit complicated, so I won't be going over it here. And then each decision tree also arbitrarily selects only some portion of these features to look at all. So if we have capital M features, then each of our little decision trees will take some number smaller than the total number of features that we have in our data. And this is known as feature randomness. It forces more variation amongst the trees, thus ultimately lowering correlation across trees and producing more diversification. And as it turns out, this produces more accurate overall results once we make the model and apply it. And then finally, we take a given piece of data, we have it be classified by all of our decision trees that we made, and then whichever class was chosen the most overall is considered the result of the prediction for the random forest model for our piece of data. So I found a neat diagram online that sort of showcases this a little bit better, where we have our random forest, which is made up of little n trees. And we take our piece of data, we send it through each of these trees. Each of the trees spits out some kind of result. And then we gather the results of all the trees together. And then by majority voting, we obtain our result for the prediction for that piece of data for our random forest. And then the other classifier I'm going to talk about a little bit, it's called naive Bayes. The naive Bayes classifier is a collection of simple probability-based classification algorithms based on Bayes' theorem, which Bayes' theorem is listed right below that, which is saying that if we have 2 sort of like events, for example, if we say that capital A represents that it's cloudy outside, or rather capital A represents that it's raining outside, and capital B represents that it's like there's thunder going on outside, then we could say that the probability that it's raining So probability of A being true, given that we have event B being true, can be expressed as the probability of B being true, given that A is true, times the probability of A divided by the overall probability of B. And so in a classification problem, however, we are trying to obtain the probability that some object/thing is a member of a particular class given some large number of known values. So we might be trying to classify, or in a classification problem, we're trying to classify, for example, if like a given wine is a red wine or a white wine, given a bunch of different like acidity number, like alcohol content, all sorts of other input data. And so if there are plenty of variation / possible values for the input data, then using Bayes' theorem in complicated problems is not very practical if we are basing our results on probability tables. So if we look at the equation listed at the bottom, what it's saying is the probability that our piece of data is in some class capital C sub k, given that our set of given that we know our set of data X is true, and then we can write out Bayes' theorem for that. And our biggest issue from here is that on the right side of this equation, we see that we have the probability of all of our data being what it is, given that given that we know that some like piece of data is in a particular class CK. And the issue here is that if we have a really large number of variables X here, so like X1, X2, X3 through, like X20 or X25 or some large number, then we might not have one single example in our data of where we have a white wine with these 20 traits being exactly these numbers. And so we're seemingly a little bit stuck with Bayes' theorem here for real life complicated problems. However, we choose to make an assumption, which is where the naive part of the algorithm comes from. And we make the naive set of assumptions of conditional independence. We assume that all features in X are mutually independent, conditional on the category CK, which is described by the equation below. So basically what we're saying is that we assume that the probability of one feature being what it is, given that we know all of the other features and the class that something belongs to, is just equivalent to the probability of having that one feature have its value, given that we know that our data is in a particular class. So we're basically assuming that every variable, part of our big like variable X, they're independent of each other, which isn't a particularly great assumption in a lot of data, right? Like if our big X consisted of just X1 and X2 being like the height and the weight of a person, then you clearly know that the height and the weight of a person aren't completely independent of each other. But we choose to make that assumption. And so what this lets us do is then we can rewrite the probability we were looking for at the bottom here. So the probability of a piece of data being in a given class CK, given we know some data X is true, can be written as proportional to the product of the probability of Xi given CK. And these data points we can actually grab, at least in a large enough sort of data set. And this is what allows us to make a classifier based on Bayes' theorem, even for complicated problems. All right, so now I'm going to briefly talk about some of the tech stack here. Again, we're going to be using Cassandra. Apache Cassandra is an open source distributed NoSQL database designed to handle large volumes of data across multiple different servers. Cassandra clusters can be upgraded by either improving hardware on current nodes, which is called vertical scalability, or adding more nodes, horizontal scalability. Horizontal scalability is part of why Cassandra is so powerful. Cheap machines can be added to a cluster to improve its performance in a significant manner. Also, just want to mention that the demo is the same demo as from 3 weeks ago. It runs code from DataStax, and they use DataStax Enterprise version of Cassandra, not the open source version of Cassandra. And Spark is also run together with Cassandra in DataStax Enterprise, which is neat. And Apache Spark. Apache Spark is an open source unified analytics engine for large scale data processing. It provides an interface for programming entire clusters with implicit data parallelism and fault tolerance. So seems like a good match for Cassandra. And we're going to be using the Spark Machine Learning Library, or MLlib, which is Spark's machine learning library. It features many common machine learning algorithms, tools for modifying data in pipelines, loading saving algorithms, various utilities, and more. And the primary API used to be RDD based or resilient distributed data set based, but they've switched over to being data frame based in Spark 2.0. And finally, this demo also uses something called Jupyter or Jupyter Notebooks. Jupyter is an open source web application for creating and sharing documents containing code, equations, markdown text, and more. And you can visit their website, see what's up. It's very popular among data scientists. The GitHub repo, which will be demoed in this presentation, contains a few different Jupyter notebooks containing sections of Python code, along with explanation/narration of the general idea of the code. And Jupyter notebooks can be used with programming languages other than Python, including R, Julia, Scala, I believe that's where the name comes from, and many others. Before I continue here, I'm going to run my docker compose command, because this is going to take a couple of minutes, or oh, okay. I already have it running. Okay, great. So finally, we talk a little bit about the demo project. Here's a link to the repository. It contains a Docker Compose file, which will run 3 separate Docker images. One will be DataStax Enterprise, which is the DataStax Enterprise version of Apache Cassandra with Spark. Then we'll also have Jupyter and PySpark Notebook running, and DataStax Studio if we want to more, I guess, directly interact with our Cassandra database. But we will not be looking at that today. And then the GitHub repo contains a lot of example files, but we'll be primarily looking at 2 examples whose theory we discussed in this presentation. The 2 examples being random forest classification and naive Bayes classification. And one note that if you download this repository, then you need to change one particular line. So if we go to the repository, and then we go to the Docker Compose file in the main directory, then we can see that there's a line right here, line 28, dealing with PySpark submit args. You need to change this line to the thing that I have written down right here, because whenever this demo was originally made, this version of the DataStax Spark Cassandra connector used to exist and used to be hosted online. This is not the case anymore, so we just need to use a different version of the Spark Cassandra connector. But once we change that, then the demo should run no problems. So once you have the demo running, or did not mean to do that, we go to the demo, and then listed right here is the port number you need to access the Jupyter notebooks. I've already entered the password, so I don't need to enter that at the moment. And so we're going to look at this random forest notebook. And what's also really cool about Jupyter notebooks in general is that if they're properly annotated, then they're very shareable, and you can just send somebody a notebook and they can go through every individual cell, take a look at what's happening in each cell. You don't have to run it all at the same time. You can run it all one by one. And that's pretty cool. So first we import some wonderful libraries. I have a helper function. We connect to Cassandra. If you just booted up the demo, then this line might not execute, or rather even line number 4 won't execute. You might have to wait a few minutes for Cassandra to spin up properly, but that's why I've ran the Docker compose command before the presentation started this time to not have to wait a few minutes. So then we create our tables, rather our one table. And so the data set that this random forest notebook looks at deals with white wine and red wines. So if we go back to the repository real quick, I believe it's under Jupyter, then under data. So this is an example of some of the data that we're looking at. There's a bunch of data for red wines, where the last categories are quality label. You see we have some 5s, some 6s. There's a 7, there's a 4. Okay. And there's also a similar data file for white wine. But what we're basically doing in this notebook is we're taking both of these data sets and we're kind of combining them into one. We're not really caring whether it's a red wine or a white wine. We're putting them together. This might take a minute as we're inserting data into our database. There are a few thousand lines, and with me running this in a low resource virtual machine, okay, I guess that didn't take too long. Then we connect to Spark. And we read in the data that we just put into Cassandra. So maybe in a more real world application, your data is already in Cassandra, so you wouldn't have to do any of this data importing stuff. Table wine row count. Okay, there we go. So we have a total of 6,500 wines to do some kind of machine learning on, right? And so we can take a brief look at the data now that we have it also labeled. You can see we have the quality column that I was talking about earlier, along with a bunch of other columns and like alcohol content, chloride concentration, citric acid concentration, and a bunch of other wonderful features. So next, this particular demo chooses to ignore all wines whose quality score is anything that's a 5.0 or lower. So these wines are rated with just whole number quality scores. And so when we're filtering for quality bigger than 5, we're saying we only want all of the rows where the quality value is a 6.0, a 7.0, and so on and so forth. If you wanted to, you could very easily change this to 4, change this to 3, or just remove this filtering part at all and attempt the same notebook and sort of see what happens there. And that's what's cool about this whole demo and Jupyter notebooks in general, is that they are really, really easy to modify. And if properly commented, they're easy to go through and understand what's going on at every individual section. And you can mess with it yourself. All right, next we do some basically what we need to do next is we need to take all of our features. So our features are different data columns, including like alcohol content, chloride concentration, citric acid concentration, density of the wine, etc. And we want to ignore the rating, or rather the quality rating, because what we're going to be training the machine learning model to do is to classify the wines into, based on the data, is this wine a 6? Is this wine a 7? Is this wine an 8? And so for our features that we want to feed into the machine learning model to train it on, we want to make sure to not look at the quality, because, well, it will probably very quickly identify that, oh, well, the correlation between quality and our label that we're looking for is 1-to-1, and, well, you won't be doing anything interesting if, yeah. So what we do is we vectorize all of our features into one vector, and then we make a new column in our data frame, which just takes all of our features that we care about, feeding into the model. So again, like alcohol concentration, chloride concentration, and we throw it all into one individual vector, and then we make a new column called features that has all of these vectors of all of our features. Then in this section, we split the data 80-20. So we use 80% of the overall data to train, and then 20% of the data to test our model on. You can also, change these numbers if you want to. So we can see that, right, so originally we had 6,400-ish wines, right, 6,500. Then after we filtered for quality 6 and higher, we reduced it down to 4,000 wines. And then we split that 80-20. So we have 3,200 wines to train our model on, and 833 to test our model on to see how we do. So we're going to be using, like we mentioned before, the random forest classifier with the number of decision trees that we're using as part of our random forest set to 10. This value, the value of the number of trees that you use, there is no perfect value. In some cases, more trees helps. In some cases, less trees helps. This is this is a very like case by case basis type of thing. But there is also some pretty good literature online if you look this up. And also a bunch of like data scientists and other sorts of people in these professions that show off some of their personal data with the optimal number of trees to choose based on the total number of pieces of data that they had in their data set. But in this case, by default, the demo uses 10 trees. So we're going to assume that 10 trees is a wonderful number to use. And this might take a minute because we're actually training the model here. All right. So we've trained the model. We have our label columns here, where 0 corresponds to, I believe, a rating of 6, 1 corresponds to a rating of 7, and so on. And then we have our predictions. We can see that for the 5 randomly chosen rows, we happen to predict correctly for all 5 of them. But we can aggregate all of this data together, right? Sorry, this next segment. And so we can see that the overall accuracy of this particular random forest model on determining whether a wine should be a quality 6, 7, 8, or a 9 is 73%, which I would say is pretty decent. If we look, however, at how many of each quality of wine there existed in our data set, we can see actually that most of our wines are either a 7 or a 6. And we have a test set accuracy of 73%, where random chance would give us, well, significantly lower than 73%, I would imagine. So it seems like we did all right, maybe. We can even very briefly try changing the number of trees. So what if we try like 20? I don't imagine that I understand this particular problem or application well enough, so I'm not sure whether I can predict if this will do better or not. We can, oh, okay, and we happen to do worse. So now we have an accuracy of 69.6% as opposed to our previous accuracy of 73%. So as it turns out, more trees is not necessarily better. But again, there's probably a magic number for this particular data set and for every data set, and you just need to find what works best for your data. A lot of this is sort of a trial and error process. And then we're going to just very briefly look at the naive Bayes notebook, which uses the same data, uses the same quality filtering, and what it's going to do is we're going to basically do the same exact problem and see how something like the naive Bayes model does compared to the random forest in this example. Pretty much all of the processes going on are similar, so we're going to let this entire notebook run. And that's another cool thing about Jupyter notebooks is that if you have an entire notebook of a set of commands, and assuming that if it's all run in the correct order, then it all compiles and everything exists, then you can just go to kernel, hit restart and run all cells. And what it'll do is it'll run all of your cells that contain code from top to bottom. And then you can just look at your results. So we can see that we created our tables. Data just got imported. Again, this particular example also aggregates the red and white wines together. And then we also separate out the wines that have quality of greater than 5. I'm not exactly sure as to why they do that. In this demo example, it's possible that if we include all qualities, well, first of all, we make the problem more complicated because we're doing a classification problem. And so when we exclude qualities below 6, we only have to classify every wine into one of 4 categories, whether it's a quality 6, 7, 8, or 9. But if we didn't do this, and assuming that wine qualities below 6 exist a lot in this data set, then we've suddenly made the classification task a lot harder, because now we're trying to classify into, for example, one of maybe like 9 different categories. And then given that we only have 6,000 samples in our data set, this probably results in significantly lower accuracy than the 70-ish% we were getting on random forest. All right. So once again, we've put all of our data into a table. We've put together the white wines and the red wines. We've put all of our features into a new column, into individual vectors, so that we can feed them into the machine learning model. We also put labels on the data, which the labels are based on. The labels are created with this label indexer line, and it's based on the quality column. So again, we probably have that a 6 is labeled 0, a 7 is labeled a 1, and so on. And then we split up the data again into 80-20 for testing training. We run naive Bayes classifier, which comes with a Spark MLlib, which you can read about in the documentation. Also, a lot of these models, they're quite complicated. And so you can run them with very little arguments. But if you know more about the math behind the models, then you can fine tune certain sections of it if it's potentially applicable to the problem that you're trying to solve. But you can also get started with these things very easily and input very little arguments into your model. So we look at the results here. And we see that we have an accuracy of 58.2%, which, assuming we have 4 categories, right? We have quality 6, 7, 8, and 9. And if we were to randomly choose, we would have probably a lower accuracy than this value. So yeah, in this particular example, we see that random forest did significantly better than naive Bayes. This doesn't say anything inherently about either random forest or naive Bayes. In particular, might have to look at the documentation for naive Bayes, maybe figure out more of the math behind it, and then maybe use some other different arguments or change up something about the model, and that may significantly improve results. Random forest also, I guess, may have gotten pretty lucky. I mean, although our data set is something like 4,000 something wines that have a quality of 6 or higher, so getting a luck of 75% over 4,000 is not very likely. But yeah, I highly encourage anyone that has never even done any machine learning anything to run these notebooks to check it out. It's pretty well described. Or like all of the individual blocks of code are labeled pretty well. And then you can make very simple changes and get drastically different results. Like I had modified the number of trees from 10 to 20 and lowered my accuracy by 5%. That wasn't a very good change, but it was a change that I happened to decide to make at that moment. And it is very possible that the accuracy could have increased. But I'm assuming another reason that the demo notebook has the default value of 10 is that to sort of make this machine learning thing seem like maybe better than it would be if you just randomly use these methods and models on your own sets of data, is they probably tried a bunch of different numbers of trees and then saw, oh, well, 10 seems to work the best or close to the best, so we'll set the default number to 10, right? And I believe that is all I have for today. Also, have a nice large list of resources that I consulted when doing research for this. Highly recommend reading some of these. Also, for math explanations, I highly recommend reading Wikipedia articles. Mathematicians seem to really like Wikipedia and really want Wikipedia's explanations and equations to be very, very, very correct. So all math stuff in general on Wikipedia is probably very accurate. All right. If we have no questions or comments, then I believe we can end.
All right, thanks, Nikita.
Yep.
I guess what are some of the newer applications you've seen for machine learning coming out right now?
I might I guess I don't know of like maybe a specific new applications. I mean, drug discovery hasn't been done for that long, at least not with like very good accuracy. I also know that like in the world of computational chemistry, for example, one very important problem that people try to kind of look at, or some brief subset of very smart computational chemists look at, is the arrangement of a particular protein around another given protein, or like around a ligand in like some maybe portion of the body, or just around like some other molecule in general, and what the preferred orientation and like arrangement of all of the like key groups on the protein would be in like an optimal energy configuration. And recently there was this thing where a group of people from maybe Google, I could be wrong on that though, but basically they applied machine learning to this task of trying to figure out optimal orientations of very complicated proteins and molecules. And they got, first of all, they got significantly increased accuracy of positioning of all the different like groups of the protein or ligand. And also they got like way faster computation of computations of, or rather predictions for the structures of these molecules, which is really cool that you both speed up the process but also make it more accurate at the same time by doing this machine learning magic, so to speak. So that's pretty cool.
It's cool. Look forward to see what comes out of the machine learning world.
All right.
All right, thanks everyone for attending. Doesn't seem like we have any more questions, so you can go ahead and stop the recording, and I'll see you.